Welcome to Unit 3, Lesson 9. We are going to be working on trig identities. I think that as far as the trig unit goes, this is my favorite lesson to do. I know you don't care. You're probably sitting there thinking like, great, this is going to be the most hardest one to do. But no, it's not. It really is simple. If you like doing like those Sudoku puzzles or whatever, I'm just solving little things. This is for you then, okay? If you're like-minded like that, then you'll be okay. And the reason I have this slide up here first is these trig identities they come in handy so much, especially this first one here, okay? In this first one here, and we'll get into it in a little bit, but that first one there, it's basically trig's version of the Pythagorean Theorem. That's why this is called a Pythagorean identity. And you can change it, like you can subtract cosine from both sides. You can subtract sine from both sides, but we'll get there. We'll get there. Don't worry. Don't fret. So the first thing I want to point out are the reciprocal identities, okay? And you're going to see these quite a bit when it comes to, simplifying or changing trig, okay? And you'll understand what that means when we get to a few problems because, like I always say, understanding the explanation is one thing, but being able to apply it is a completely different level, and if you could do that, then you are good to go. So, this first one here, this CSC, that stands for cosecant. Cosecant, I'll be okay. That's how you spell. Now, that is the flip, that is the reverse of sine, meaning cosecant is the same thing as 1 over sine. It is the reciprocal of sine. We'll put an X here because it's an X right here. So if sine is some old hoe, right? If sine is O over H, and cosecant is the flip of that, cosecant would be H over O. So literally, if I had a triangle, 30, 60, 90, 45, 45, 90, cosecant is the flip of sine. So it's H over O. Same rules apply. You do it the same way. You label your sides. You find out which side is opposite, which side is adjacent, which one's a hypotenuse. And then you put your hypotenuse over your opposite, which is the reciprocal of sine, because that's what cosecant is. It's the reciprocal of sine. Now, for our sake, for proving things, we would probably want to change anything that's cosecant to 1 over sine. All right? So the side ratio is if you have a triangle, a right triangle, and you're trying to figure something out. This is kind of more for proving. I say proofs. You can say solving, whatever. But we really don't do proofs like we do in geometry here. But you'll see the difference as we go forward. Okay, secant. That's secant. All right, that is the reciprocal of cosine. Okay, if cosine, all right, if cosine is caught another hoe is adjacent over hypotenuse, secant is the flip of that. It is hypotenuse over adjacent. So if I have a triangle and I know the sides and I have the values, I just create this fraction, hypotenuse over adjacent. If I'm proving or solving or whatever, I probably want to change every secant to 1 over cosine most of the time. All right? Now, last but not least, we have cotangent. Cotangent. All right? That is the reciprocal of tangent. That seems to be the one that everybody remembers. And I'll get back to that in a second. So if tangent, tricking on Alexander, is opposite over adjacent, cotangent is adjacent over opposite. So if you know your sine, cosine, if you know SOHCAHTOA, then you will know these because of the flip. The only thing that's going to help you remember is this. Okay, my cosecant is the reciprocal of sine, all right? My secant is the reciprocal of cosine, and my cotangent is the reciprocal of tangent. Here's what everybody wants to do, okay? Everybody wants to say, oh, this is a C, and this is a C, so my C's must go together, so cosecant is the reciprocal of cosine. No, stop. Don't ever do that. Okay, the S's and the C's always go together. We always have sine and cosine, right? You always need an S and a C. So my cosecant is the reciprocal of sine, all right? Same thing here. Everybody sees the S, and they want to make secant the reciprocal of sine. It is not. Secant is the reciprocal of cosine. All right? That's the one mistake when everybody's doing this. They kind of, that gets them. So you really got to put some thought into this and make sure you know this, okay? Just know which one's the reciprocal of which. Now we're going to move over here to this little box here. This is quotient identities, all right? Quotient identities. And if you recall, when we were using the unit circle and we tried to graph tangent for the first time, we figured out that tangent is really sine over cosine. All right? So tangent is the same as sine over cosine. Then remember we filled out that table because sine was always y and tangent was always x. So we kind of divided those out, and that's where we figured we had those asymptotes. My favorite math word of all time, asymptotes. Got to hit the P. So now, if cotangent is the reciprocal of that, cotangent is going to be cosine of x over sine. All I do is I flip that. All right? So why are these important? Well, for identities, okay, for figuring things out, for proving or solving things, these identities here are what we're going to be working on, these two things here. These would help us in previous lessons if we ever had to find the actual ratio or fraction of cosecant of an angle on a triangle, which we're not doing that today, okay? So we're going to be using these identity ones more so. Here we go. Okay, so let's do some of these things. Let's actually apply these things and you can see what this whole big spiel is about, okay? Directions. Use the reciprocal and quotient identities to simplify the expressions below, okay? So we have some expressions, we're simplifying them. It's not asking us to find the sine of any angle in a triangle or anything like that. We are simply simplifying them, okay? That's the difference between using SOHCAHTOA and the identities below here. So my advice to you is whenever you have these things, 95% or 99% of the time, you want to change everything so that it's in sine or cosine form. Okay, so make a little note here. Change to sine and cosine form. Things tend to simplify real easy. The only time you wouldn't change to sine or cosine is if you were to see sine squared plus cosine squared equals 1. And it's one of those identities. But we will get there, all right? So let's just practice the easier stuff first. So what I'm doing for example 1 is I'm taking cosecant and multiplying it times tangent, and then multiplying that times cosine. So cosecant is a reciprocal of sine, so it's 1 over sine. Tangent is sine over cosine. And cosine, well, that's just itself, cosine over 1. Now, notice I didn't put the x's in. I probably should. My final answer, I better put the x's back in. Some people just use S for sine and C for cosine, which is fine as long as you can follow it. And your answer better be written out completely, okay? You can't shorthand your answer, all right? So now it's just going to get to a point where we're multiplying fractions. I can simplify tops and bottoms, meaning this sine and this sine cancel. Boom. This cosine and this cosine cancel. I end up with 1 over 1, which is 1. And that's my final answer. There are no trig functions left in that problem. All right. Let's take a look at the second one. Okay, I have cosine squared. So I'm just going to put cosine squared over 1 times secant is the reciprocal of cosine. So I put 1 over cosine. That's secant. And cosecant is the reciprocal of sine. Okay, so I just made everything into sine and cosine form right there. There are no more secants, cosecants left, anything. And I'm going to start canceling here. One of these cosines can cancel with one of these. Remember, cosine is squared. I technically have 2 cosines up there. Just like if there was an x. If I had x squared and I had an x here, one of these x's cancel with one of these. The same thing for cosine and sine. The same thing for trig. Okay? So now I can't cancel anything out. So cosine times 1 times 1 is just cosine. Sine times 1 times 1 is just sine. That is very familiar. Do you know what that is? Cosine over sine is actually cotangent. Okay, it's the reciprocal of tangent. All right? I'm going to go over here, and I don't want to leave it like this. I want to say it's cotangent of x. Okay? So if I took this original expression, and let's say I picked a degree for x. Let's say for these x's, let's say I put in 45 degrees. I took the cosine squared of 45 degrees times secant of 45 times cosecant of 45. That would give me the same exact thing as the cotangent of 45 because they're the same. It's just simplified. They're the same. All right. On to the next one. What do we got here? Okay, ooh, a fraction. So I'm going to work with the numerator first. I have sine, which I'm going to leave alone. Put that sine over 1. Times, that's sine. Secant is the reciprocal of cosine. So I'm going to do that. All over tangent really is sine over cosine. All right? So now let me do my math operations on the top. I'm going to multiply those two fractions. Sine times 1 in the numerators is sine over cosine times 1 is cosine. All over sine over cosine. It looks like I have something over itself. Anytime I have a fraction and I have the same thing on the top and the bottom, it equals 1. If that's hard for you to see with fractions over fractions and so forth, isn't sine over cosine the same thing as tangent? It is. So if I wanted to simplify this out more, and I don't have to, but if I wanted to, just to show you, sine over cosine is the same thing as tangent over, well, sine over cosine is the same thing as tangent. Tangent over tangent is 1. And there you go. All right, now you try. I'm going to do these. So if you want to pause this video and try these on your own, go right ahead. Because I'm about to rip through them, go a little bit faster. Not too much faster, but a little bit. And we'll go from there. So I'm going to leave my sine as sine over 1. My secant is 1 over cosine. And my cotangent is cosine over sine. Okay, I'm multiplying these all together. What can I cancel tops and bottoms? Top sine, bottom sine. Top cosine, bottom cosine. I end up with 1 over 1, which is 1. And I'm done. You can see why I like doing these things. I like just breaking things apart and just canceling everything out easier. It makes me feel, I don't know, math makes me feel smart in general, knowing how to do it. It should make you feel smart as well. It should never make you feel not smart. Okay, if it does, you just need to work a little bit harder to get it better, and then you'll feel smart. All right, next one. Sine squared over 1. Secant is the inverse of cosine, or reciprocal of cosine, and cosecant is the reciprocal of sine. So I'm going to multiply all these bad boys together and see if I can cancel anything. This sine cancels with this. It's one of those signs, not all of them. So I have sine on the top times 1, which is sine. Cosine on the bottom, denominator, times 1, which is cosine. And sine over cosine is tangent. So make sure you put your x back in there. Just a point to note. We've seen this happen a couple of times. We've seen sine and the square is in between sine and x, okay? And we've seen it here. And number 2, the square symbol, like the squaring, is in between my trig function and the degree. So it's cosine 2 of x. Why do they do that? Let me just explain that right quick here. If you see this, you have sine, and you see a little 4 here, and an x, okay? In the calculator, you cannot put a 4 there. Once you hit the sine button, it immediately does this, and it waits for you to put something there. Let's say you put your x here. You cannot put anything right there in the calculator. This sine 4 of x, that's the same thing as taking the sine of x and taking the whole thing to the power of 4. All right? So why do they do that? Because if I write something like this, you might say, wait, is this either the sine of x, the whole thing to the power of 4, or is it like saying sine of x to the 4th? It's order of operations. Do I apply my exponent to my degree first, then take my trig function second? Or do I take the sine of x first, then do I do my 4th power second? Okay, how do you figure that out? You put the number right here. When my students get to calculus, whenever they see this, I tell them right away to change it like this, because we got to do things with the exponent, like bring it down, whatever. And I want them to make sure they know that that's an exponent for the whole thing. Okay? So when you see something, all right, notice when I get rid of the x, you know how I don't write the x? It makes it a little bit easier. That you can definitely tell at sine squared you have 2 sines. You're not squaring the x. All right? But unfortunately, this is an answer. You can't just leave the x out. So just keep that in mind. Okay? I just wanted to explain that. You know what? Let's do purple. Purple's a nice color. Tangent. That's sine. I'm going to use just S and C. You ready? That's sine over cosine. Secant is 1 over cosine. And this is cosine, which is cosine over 1. I'm multiplying them all together. What can I cancel? Well, glad you asked, my friend. 1 cosine on the bottom cancels 1 cosine on the top. So now I just end up with sine over cosine. And again, that's tangent. But when we write our answer, we better write it out, T-A-N, and you better put that degree symbol there, whether it's the x or theta or whatever. Okay, don't just put tan. It's tan of x is your answer. Okay. Now, flashback to the unit circle. The Pythagorean identity. All right. That is the big one. It's sine squared of x plus cosine squared of x equals 1. But how did we get that? I'm going to show you how we got that. If you're like the type of person that says, I don't care how we got it, if I'm never going to have to prove how I got it, if all I got to know is this is a rule, as long as I know this, sine squared plus cosine squared equals 1, I'm fine. Okay? So if you're that type of person, that's okay. You can really just, you know, drift off into your imagination for the next 10, 15 minutes while I explain where that comes from. But it's really simple. I'm not going to get crazy, even though this diagram just is so intimidating right off the get-go. All right? So first off, this is the unit circle. Okay? It has a radius of 1, right? You see the 1s here? Okay, so this radius, which happens to be my hypotenuse, is 1. Okay, isn't the Pythagorean theorem, isn't that a squared plus b squared equals c squared? And for the case of our unit circle, if I have a triangle here, right, we can say that if this is one of our legs, that's the same thing as a from our Pythagorean theorem. This is the same thing as b from our Pythagorean theorem. And this is c, because c is always a hypotenuse, always the 90 across from the 90-degree angles. So if we have a right triangle, my 2 legs, a squared plus b squared equals c squared, all right? So where does sine and cosine come in? People, don't you remember that cosine is always the x-coordinate of a point on the unit circle? And sine is always the y-coordinate for a point on the unit circle? So if cosine is my x, this movement to plot this point, this is my x movement. That is cosine, right? This upward movement is my y movement, which is sine. So if I'm going to use sine and cosine to figure out the Pythagorean theorem, a squared, which is my y value here, it's sine squared, plus b squared, which is my x value, which is cosine, equals my hypotenuse squared. My hypotenuse is 1. This is the unit circle. 1 squared is 1. Okay, so that's how we get this. And it just goes down to the basic things we've learned before. Okay, cosine is always my x, so it's this movement. Okay, sine is always my y, so it's this movement. And my hypotenuse is 1 in the unit circle. 1 leg squared plus another leg squared equals a hypotenuse squared. That's what this is. And all we did was substitute our values in. Okay, so that's how the Pythagorean theorem works. Now, you might not see it written like this. For example, if I had an equation, let's get rid of trig for one moment here. And I just want you, you don't have to write this down, I just want you to watch this here, what I'm writing in black. If I have 3 plus 1 equals 2, yeah, I'll be okay. That's minus 1 equals 2. But let's use 4. Okay, I was already subtracting the 1 from 3 if I moved it over. Anyways, 3 plus 1 is 4. Can I also say, if I subtract 1 from both sides, can I say 3 equals 4 minus 1? I could. What if I subtracted 3 from both sides? Okay, I minus 3, I minus 3. I could say 1 equals 4 minus 3. Both of these are still true as this is, right? What I do to one side of an equation, I have to do to the other. That is the basis behind solving for a variable. Using opposite math, yes? Yes. So, we're going to use that right here. What happens if I subtract cosine from both sides, right? Cosine squared, rather. I would get sine squared of x equals 1 minus cosine squared of x. All right? Same thing happens. What if I subtracted sine squared from both sides, not cosine squared from both sides? I would get cosine squared of x equals 1 minus sine squared of x. So why are these important? Because sometimes you might see this in an expression that you got to simplify. Well, this equals 1. I can substitute 1 in for sine squared plus cosine squared. But sometimes in equations, they get tricky with you. They give you this. And you're like, me, how am I supposed to do that? Well, this, you can put sine squared in for. Sine squared is 1 minus cosine squared. What if they give you, and I think you know what I'm going to do now, what if they give you this, 1 minus sine squared of x? Well, that's the same thing as cosine squared of x. I can substitute that in. All right? Now, I used to have a student who used to do this. If they had 1 minus cosine squared, all right, they said, I'm like, oh, that's a sine squared. They're like, I don't just convert it. What I do is, I know 1 is sine squared plus cosine squared. So what I'm going to do for my 1 here is I'm going to say that's sine squared plus cosine squared, because that's what 1 is. 1 is sine plus cosine squared. And then I still have minus cosine squared. And I don't know, my plus cosine squared and minus cosine squared cancel. So I have sine squared. If you want to do that, that's fine. If you want to substitute sine squared for cosine squared for every 1 you get, that's fine. But don't forget, you still have your minus cosine here, so you got to write minus cosine afterward. And then your cosines cancel. And you still end up with sine squared. For me, if I see this right here, well, I just know that's sine squared without doing any of the additional algebra work. But look it, you could do it any way. I was actually impressed with the way that kid showed that to me. His name was Nico, and it worked for him. So if it worked for him and you can algebraically use this and prove it and it was fine and correct, go for it. So the first set of simplifying expressions we did not involve the Pythagorean identity at all. Okay, these ones do. Okay, these ones do. So we're going to go through these, and I think this is going to be a great place to stop after these 3, because there's been a lot of explanation and remembering and, you know, that sort of thing. So let's finish these 3. We'll stop. We'll call it a part 1, and then we'll do Unit 3, Lesson 9, Part 2 at a later time. All right, so let's start. Okay, right off the bat, I see sine squared plus cosine squared. Okay, this is equal to 1. Okay, so I'm going to say 1 over sine of x. I know that's a reciprocal function. I know that equals cosecant of x, and I am done. Visca, how did you know that? Because we need to get good at knowing our reciprocal functions. Okay? There we go. Now, there is another way you can do this. It's the way I just did it was the easier of the two ways. Here's another way. The other way might be easier to you, but it's a little bit more writing. You can break this up literally. Now, you know what? I'm not even going to go there. Not even going to go there because it involves another trig identity, which you guys, I don't want to show you right this moment. Okay? So, here we go. Are you ready? Example 2. 1 minus sine squared. I think that's the same thing as cosine squared. And it is. It's the same thing as cosine squared. So, I'm going to say cosine squared over 2 cosine. All right? They use a instead of an x or theta, and that's fine. So now I can cancel. I can cancel one of these cosines with one of these two. So now it's just cosine of the first. So what I'm left with is cosine of a over 2. That cannot be simplified anymore. If you want to rewrite that, technically that's 1 cosine. I can write 1/2 cosine of a. Either way would be fine. All right? You are good to go there. Either way would be fine. And last but not least, example 3. Sine squared of b over cosine plus cosine of b. Technically, this cosine of b is over 1. If I could combine those two fractions into 1, that would make life easier. And what I'm going to do is the following. All right? Not only do I want to combine these to be 1 fraction instead of 2, if I can, and also I see a sine squared. If I could make a cosine squared over there, because there's no way I can get a sine on the bottom to cancel with that. Okay, there's nothing I could do. But what if I multiplied the top by cosine, and what I do to the top, I need to do to the bottom, right? Now I'll have a common denominator, meaning I'm going to use just letters here. Sine squared over cosine plus cosine times cosine is cosine squared over cosine. Now I can combine these. When I add fractions, the bottom stays the same. Okay, you need to have a common denominator, and it will stay that common denominator. So the top is just going to be sine squared plus cosine squared. Oh boy, that's our Pythagorean identity. That is, this numerator is 1 over cosine. That's reciprocal. That's secant, and they use the letter b. So it's the secant of b. And you are done.